In our previous section, we looked at our coordinate system, we looked at functions, we looked at graphs, different types of graphs. In this section, our focus is going to be on what we call linear functions and their graphs. So a linear function is just an equation. So it's going to be a linear equation whose graph is a line. Now we talk about a linear equation. It's of the form ax plus by equal to c. But you may not see the equation written in that form. So really a linear equation can be written in this form. A and B cannot both be 0, otherwise this will just say 0 is equal to some number c. So here our A, B, and our C are just real numbers. The x and the y are our variables. An important part of linear functions or linear equations is finding the intercepts. So when we talk about the x-intercept, that's where our graph will intercept the x-axis. And how you figure out that point is you put in 0 for the y value, and then you solve for the x to see where the x intercepts the x-axis. If you want to find the y-intercept, or where the y intersects or crosses the y-axis, then you put in 0 for your x value, and then you solve for your y. So we're going to use intercepts to graph the equation 2x minus 3y equal to 6. So the first thing we want to do is we want to find our intercepts. Oftentimes what I'll do is I'll just make a table of values where I'll put in an x value and I'll get back a y value, or I could put in a y value and get an x value back. So to find my x-intercept, I put in 0 for y. In my equation, that means it's going to be 2x minus 3 times y is 0 equal to 6. And the 3 times 0 is just 0, so I'm just going to cross that out. And this becomes 2x is equal to 6. So dividing both sides by 2, you have x is equal to 3. So the point is going to be 3, 0. So x is 3 and y is 0. To find your y-intercept, you put in 0 for x. If x is 0, this is going to be 2 times 0 minus 3y is equal to 6. So again, the 2 times 0 is just 0. Don't forget there's a minus in front of the 3y. So this is negative 3y equal to 6. And if you divide both sides by negative 3, y will be equal to negative 2. So the point here is x is 0, y is negative 2. You only need 2 points to graph a line. So I could graph the line right now. Oftentimes what we do in math is we do a third point just to check. Now if you want to check for a third point, you're just going to put in a value for x or y. And I'm just going to put in 1 for x because I haven't really used that yet, and 1 is a fairly small number. And I'll get 2 times 1 minus 3y is equal to 6. 2 minus 3y equal to 6. And if I subtract 2 from both sides, then the 2's are gone. This is simply negative 3y equal to, remember we're minusing negative 2, or minusing 2, so this is going to be a positive 4. Which means that y is going to be 4 over negative 3, or negative 4/3. And that's fine. Now I don't want to graph negative 4/3 because that's kind of hard, it's an improper fraction. So I'm going to write that as negative 1 1/3. So if x is 1, y is a negative 1 and a little bit more. So notice that all 3 points line up. And that third point that I figured out, I just used it to double check my math, make sure my math is good. The important points would be your x-intercept, the point 3, 0, and the y-intercept, which is a point 0, -2. So we've used the intercepts to graph this equation. Probably the most important part of a line is its slope. So I know you've seen this formula before, that if you have any 2 points, x sub 1, y sub 1, x sub 2, y sub 2, then to find the slope, and we use this m to indicate slope, would be one way to say slope is the change in y over the change in your x values, or you've heard the term rise over run. When we talk about how y changes, it's a subtraction. You're subtracting your y values. So it'd be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Just a note that it really doesn't matter the order here. You could also use y sub 1 minus y sub 2 over x sub 1 minus x sub 2. The key is that the y's are on the top, the x's are on the bottom. And if you look at the columns, the y1, x1, that's 1 point. y2, x2, that's 1 point. So the important part, y's over x's, and then the individual points would be the columns. Let's go ahead in example 2 and find the slope of the line passing through the points. We're also going to graph the line. Right away, I could actually graph this line because I do have 2 points. But if I didn't have a graph, then to find the slope, what I could do is simply call the -3 for my x sub 1, y sub 1, the -4, -2, x sub 2, y sub 2, and use my slope formula, which says it's y sub 2, or -2 minus y sub 1 is 4, x sub 2 is -4 minus x sub 1 is a -3. So a lot of times people mess up on that double negative, minusing a negative. At this point, slope is going to be a -6 over, so this is -4, and it turns to a +3, change, which would be a -1. And then I would never leave it like that. It's simply 6. So that would be the slope of the line. Now remember I said it doesn't really matter if you do y sub 2 minus y sub 1 or y sub 1 minus y sub 2. So let's just say I changed the order. And I did y sub 1 minus y sub 2. So that would be a 4 minus a -2 on the top. On the bottom, it would be x sub 1, -3 minus y sub 1 would be 4. Oops, and I did what I said not to do, minus a -4. Okay, so on the top it's going to be 4 plus 2, which would give me a +6. In the denominator, it's going to be 3 minus a -4, or -3 plus 4, and that would give me a +1. So I still get a +6 for my slope. If I were to graph these points, I have -3, +4, so up 1, 2, 3, 4, and I have -4 down 2 to -2. So this is a very, very steep line. Another way that we can find the slope without using the formula is if we already had a graph and we're looking at nice points. So when I say nice points, I mean integers, not fractions. So if you look at our 2 points, what you could do is you could simply count. Remember what we're going to do is we're going to do rise over run. So you could choose any point to start with. I'm going to choose this lower point, which would be the -4, -2. And I'm going to rise and count. I'm going up 1, 2, 3, 4, 5, 6. So since I'm going up a positive 6, remember the slope is your rise in this point. At this one, it's a positive 6 over the run. The run is the x values. So I'm going to go 1 to the right, so that's a positive x value. And this is simply 6 over 1, or 6. Let's do another example. I can see the point 4, -2, -1, 5, that I could use a formula. I could call this my x sub 1, y sub 1, and then x sub 2, y sub 2 for the -1, 5, if I choose to. You don't have to do that. You could simply look at it and do the subtraction. So mathematically, if I was going to find the slope, I could do the y sub 2, which is 5, minus the y sub 1, which is a -2, over the x sub 2, which is -1, minus x sub 1, which is 4. So this is going to turn into 5 plus 2, or 7 over the -1 minus 4 would be a -5. And when you're dealing with fractions, where you put the negative doesn't matter. The negative can go in the denominator. The negative could go in the numerator. Or the negative can simply stay in front of our fraction bar, which is typically where my lab wants you to put it. I computed the slope, and it doesn't matter how you write it. I'm going to go ahead and graph. So we have a positive 1, 2, 3, 4 for the x, down 2 for the y. A -1 for the x, a positive 1, 2, 3, 4, 5 for the y. And our line passing through these points we've graphed. Let's go ahead and double check our math using these two nice points to count our slope. Again, it doesn't matter which point you start with. You always want the y's over the x's, so rise over run. If I start with the point 4, -2, then I go up 1, 2, 3, 4, 5, 6, 7. So it's a positive 7. But I'm going over to the left 1, 2, 3, 4, 5. So that's in the negative x direction, which means if I were to count to find my slope, it would be 7 over -5, which is what we got. The next thing we want to talk about is the slope-intercept form of a line. And that's the only form that your textbook uses, although there is the point slope form. But we're just going to restrict our conversation to slope-intercept form. So the slope-intercept form of the equation of a line is your y equal to mx plus b. So m is your slope, b here is your y-intercept. And remember, to find the y-intercept, you're putting in 0 for your x value, which is why the y-intercept will always be 0, comma, and then the b value is the y value. So if we were to graph using the slope-intercept form, what we would do is we'd start out with our y-intercept because it's there in the equation. And then we would take our slope and we'd count to find another point, and we'd draw the lines through the 2 points. In example 3, we're going to graph by using the slope and the y-intercept. Notice that this equation is in slope-intercept form, where the 2/3 is your slope m. Remember, the slope does not include the x value. It's just the number 2/3. I want to make sure that if my slope is a whole number like 2, or an integer like -3, that I write it as a fraction and put it over 1. Because when we count, we always want to count places for the y and for the x value. So your slope should always be written as a fraction. Now our b value here is -1. That would be this last number. So we include the negative if it's there. If it's a plus, it would be a positive 1. b is equal to -1. and that would be my y-intercept. As a point, that would be 0, -1. Graphing, I'm going to go to 0, -1, and I'm going to start with the point, which is my y-intercept, and then I'm going to use my slope to count. So my slope is 2/3, which means I'm going to go up 2 in the positive y direction, and I'm going to go to the right 3, 1, 2, 3. That gives me my second point. This would be my line. So, oh, that's a sad looking line. If your equation is already in the slope-intercept form, it's a very simple graph. Also note that you could use, instead of 2/3, if you put a negative 2/3, that's still the same slope because it simplifies to positive 2/3. So let's say that I use negative 2/3. I would still start at the point 0, -1, which is my y-intercept. But this time I'm going to go down 2, and then I'm going to go to the left 3, 1, 2, 3. So you could see that these points will line up, although I hand drew that line, so it's a little off. In this next example, we're going to continue to use the slope and the y-intercept to graph. However, you should note that the equation is actually not in the correct form. It's not in the y equal to mx plus b form. So we're going to have to get it into that form. The first thing I'm going to do with this equation, 3x plus 4y equal to 0, is I'm going to subtract 3x from both sides to get the y term by itself. So again, the 3x's will go to 0 or cancel, and I have 4y equal to -3x. Dividing both sides by 4y is equal to a -3/4 times x. So this is y equal to mx. There's no b value there, but since there's no b value, then my b value is going to be 0. So the b value is 0, which means my y-intercept is x is 0, y is 0. And the -3/4 would be my slope, m. Here you need to choose if you want the negative in the numerator or the denominator. Since we're going to be graphing, negative indicates direction. So you can have -3 over a +4, or you could have a +3 over a -4. It really doesn't matter which one you choose, but you have to choose one. Let's graph. We have our y-intercept, which is the point 0, 0. Now, if we use the slope of -3/4, that means I'm going to go down 1, 2, 3, and to the right 1, 2, 3, 4 to get my next point. But let's say we're at our y-intercept 0, 0, and we decide to use a slope of 3 over -4. That means I'm going to go up 1, 2, 3, and to the left 1, 2, 3, 4. Notice that all these points line up because it doesn't matter if you put the negative in the numerator or in the denominator. So I've used the slope and the y-intercept to graph the line, but I had to do a little bit first. I have to get it in the proper form. Something I did want to talk about is what the slope means if it's negative or positive. Notice that our slope is negative, which means as you go from left to right, the line falls. So a falling line means negative, it goes down. If your slope is positive, as you look from left to right, the line should rise or go up. However, there are two special lines, horizontal and vertical lines, that don't have negative or positive slopes. So the horizontal line only has a y value in the equation. Vertical lines only have an x value in the equation. Example 5, we want to graph y is equal to -2. I notice that there's only a y value in that equation. Now, in the beginning, I said that linear equations are of the form ax plus by is equal to c. So if you look at y is equal to -2, can I write it in that form? Absolutely. 0 times x plus 1 times y is equal to -2. And I've written this equation as a linear equation. So yes, the graph is going to be a line. However, the equation says y is equal to negative 2. Since there's no x value, it doesn't really matter what x is. Y will always be negative 2. So if you don't remember that this is a horizontal line and you simply go to y equal to negative 2 and draw your horizontal line, then what you could do is you could make a table of values. So notice there's no x value in my equation. X can be anything. What if x is 0? What is the y value? Well, the equation says y is equal to negative 2. If x is 1, y is equal to negative 2. If x is negative 1, y is equal to negative 2. If x is a billion, y is equal to negative 2. So you could graph these points, 0, negative 2, 1, negative 2, negative 1, negative 2, and simply draw your horizontal line. But if you were to graph a horizontal line, really all you need is one point. So you could go down to where y is equal to negative 2. By the way, that's your y-intercept, and simply draw a horizontal line through that point. So let's just talk about the slope here. Notice as I go from left to right, my line does not change. So that means the slope is 0. Now mathematically, I could say use these 2 points here, 0, negative 2, and 1, negative 2. And I could compute the slope. So I would find that the slope is equal to negative 2 minus a negative 2 over 1 minus 0. So that's negative 2 plus 2 is 0 over a positive 1, which is simply 0. Horizontal lines have a 0 slope because there's 0 change as you go from left to right. Okay. So obviously the next thing we're going to talk about is our vertical line. In example 6, my equation only has x. It does not have a y value. However, I don't like it the way it's written. Notice that this is x plus 5 equal to 8. It would be really nice if I could just get the x by itself by subtracting 5 from both sides. So my x, these cancel, will be equal to 3. I could see that I'm just going to go on the x-axis to a positive 1, 2, 3 and draw my vertical line. And that's all I have to do. Again, if you don't remember that it's a vertical line, what you could do is make a table of values. So x is equal to 3. It doesn't matter what y is. If y is 0, x is 3. If y is 1, x is 3, and so on. So let's see, 3, 0, yes, 3, 1, vertical line. So now, what is the slope? Remember, what we're doing is we're describing how the line changes as we go from left to right. Unfortunately, we can't do that with a vertical line because to the left of the line, there's nothing. So I can't describe that slope. It's undefined. And to the right of the line, there's nothing. There's no graph. Mathematically, what I could do is I could compute the slope. Remember, it's y's over x's, so we'll just go ahead and use these 2 points here. 3, 0, and 3, 1. So if I take my y values, 1 minus 0 over 3 minus 3, then I get 1 over 0, which is undefined. Which is why we cannot define the slope of this line. We cannot describe how the slant of the line changes because the slant of the line does not change. The important part of a slope is what we call a rate of change. So when we talk about the slope of the line, what we're doing is we're describing how the y value changes as the x value changes. So as you go from left to right, what's happening to your graph? Is it going up? Is it going down? Is it staying the same? And that would be what the slope represents, and that would be our rate of change. Okay? So it's the rate that the y value changes. In example 7, we have this graph. It's the cost of Medicare benefits for 2007 through 2016. So we've got the starting date is 2007, it ends at 2016. So we want to find the slope of the line segment. We want to round to one decimal place, so probably going to have to use your calculator here. And we're going to describe what the slope represents in terms of this particular problem. Notice that I have points on my graph. So the 2007, that would be, oops, too thick. My x sub 1, 446, that would be my y sub 1. So that means in the year 2007, the cost is in billions of dollars. In 2007, we spent $446 billion on Medicare. The last point I have on this graph is the year 2016, which would be my x sub 2. And then my y sub 2 would be 909. So in the year 2016, we spent $909 billion for Medicare. So the question said to find the slope of the line. Our slope is going to be the y value. So y sub 2, 909 minus 446 over 2016 minus 2007. That's going to be 463 over 9 if I put it in my calculator correctly. And it said to round to one decimal place. If you take 463 and you divide it by 9, it's 51.4. If I round it to one decimal place, because it's 51.44444. Now, if it didn't tell you what decimal place to round to, then you would answer in terms of how you were given numbers. Notice that these are nice whole numbers. So if I was not told to round to one decimal place, I can assume that I would just round it to 51. And I'm going to change the equal to the squiggly lines because this is an approximation. So what does this represent, this 51.4? What it means is that every year, and here notice the slope is upward, so it's a positive 51.4. That means every year Medicare increases, the cost for Medicare increases by about $51 billion. I'll do 51.4 billion dollars. That's a lot of money. Let's look at another application with the slope. Example 8. This is another graph that has to do with healthcare. So the graph shows the average annual premium for employer-sponsored health insurance for family coverage from the year 1999 through 2008. What this represents is how much an employer would pay to give one employee family coverage. Now it starts in the year 1999. So what I'd like to do is look at this graph first and look at this first point. This first point would be my x sub 1, which is 0, my y sub 1, which is 5791. It doesn't make sense for the x value to be 0. What does that represent? So I'm going to look at this graph and look at where we're starting at. We're starting at the year 1999. At that point, my x value is 0. So that tells me in 1999, the x value is actually 0, which is why this is 0, comma 5791. And if you look at part A, it says use the points to find a function that models the average premium for family coverage x years after 99. So since x represents the years after 1999, when my X value is equal to 0, I'm at the year 1999. So sometimes with these graphs, you have to be really careful about your X or Y values, what they stand for. So in the year 2000, that's 1 year after 1999. So that's where my X value is 1. 2001, the X value is 2, and so on. Okay. So let's see. We have to use the 2 points to find a function that models the average premium for family coverage X years after 99. So I have 1 point, and then my other point is X sub 2 is 9. The Y sub 2 is 12680. So let's look at this first point. In the year 1999, which is 0 years for my X value, 0 years after 1999, the Y value is 5791. So that means in the year 1999, for an employer to pay for family coverage for one employee, they paid $5,791 per year. And these figures are actually national figures, they're accurate, I looked them up. So let's look at the ending value here on this table. X is 9, so that's 9 years after 1999. That would represent the year 2008. In the year 2008, yearly family coverage for one employee was $12,680. So it's risen quite a bit. Now, if you were to look up the national costs for family coverage now, it should be pretty high. So part A says we're going to use the 2 points to find a function that models the average premium for family coverage. So since we're going to be finding a function or an equation, remember a function's just an equation. And our graph is a line. I'm looking at a linear function or a linear equation, which tells me I'm doing y is equal to mx plus b. What's really nice about this graph is notice that when x is equal to 0, we have our b value, which would be the y-intercept, right? Because the y-intercept is when x is equal to 0, and if x is equal to 0, that y value is your b value. So I have my b value. All I need is my slope. To compute the slope, I'm going to do y2 minus y1, or m is equal to 12680 minus 5791 over 9 minus 0. I have 6889 over 9. And it doesn't tell me what to round to since the values were all given to me in nice whole numbers. I'm going to put this in my calculator, and if there's a decimal, I'm just going to go ahead and round it to the nearest whole number. So 6889 divided by 9 gives me 765.444. So it rounds to about, let me put the squiggly lines, 765. So my equation is going to be 765 x plus 5791. And that would be the equation that models this problem. It's simply just the equation of the line. Excuse me. But if it says a function, I could replace y with f of x and write it in function notation. It doesn't really matter which one you use. So that was our part A. In part B, it says use the model. Now, when it says use the model, it's just saying use the equation to project the average premium for family coverage in the year 2018. Okay, so you got to be careful here. And I'll just use the y equal to 765x plus 5791 91. Remember, the y value is the cost. That's what we're trying to find. We need to put in the proper x value. So the year 2018, that's what we want. So remember, x is the years after 1999. So 2018 is 19 years after. In other words, we want 2018. We started with 1999. So if I do the subtraction, I end up with 19. That would be the x value that I'm putting in my equation. When I plug that in a calculator, 765 times the x value of 19 plus 5791, that's going to give me 20326. Okay, so the average premium for family coverage in the year 2018, and I'm not going to write a complete sentence, it should be about, but I do need the dollar sign, 20,326 per year. And that's the real important thing about these linear functions is that you can use them to make predictions. If you have past values and it looks like if they line up to a line, you could draw the line through the points, compute the slope, come up with an equation, and make a prediction assuming that the line doesn't change. So you could, if you want to check this out, look at the national average premium cost for family coverage and see if it's about $20,000. So this is the end of this section. Really what the goal was here was to look specifically at linear functions and some important properties about it, such as the intercept, the slope, and graphing. We're not going to do 7.3 through 7.5. We're going to skip to 7.6 and expand our models and go from linear to other models that we haven't talked about yet, such as a quadratic model. So that's it for this section.